how do I want you to define the YZ plane? When you say the YZ plane, what does that mean? All the points where x is 0, right? All the points where x is 0. So the distance from the YZ plane is just going to be which coordinate? The absolute value of the x coordinate. The distance to the YZ plane. Which plane is the YZ plane, everybody? This one is the x coordinate. The distance is strictly the x coordinate. So which one has the biggest absolute value x coordinate? Which one? A, B, or C? C. Which one? It says which, oh, closest. Which one's the smallest? So because of the 0.9, right? Which one is closest to, oh, what is the XZ plane? What does that mean?
Y is 0.
That's y is 0, right? So that's where the distance, the y coordinate, which one lies on the YZ plane? Oh, which one has y is 0? B. Which one is furthest from the XY plane? What does XY plane mean? That's when Z is 0, right? So the distance for Z, which one is furthest? Which one has the biggest absolute valued Z coordinate? Oh, it's B for all three of them. Wonderful. Okay, so this is the one I want you to do by yourself. Read this, but only go to this right here. I want you to answer that question right there. Don't worry about the rest. Just go to there. How many coordinate planes are there? There's the XZ plane, and that's when y is 0. There's the YZ plane, and that's when x is 0. And then there's the XY plane when z is 0. So what do? You have three states. You write out the three states. So when y is 0, what do you end up with? X minus 1 squared plus 0 plus 3 squared plus z minus 2 squared is equal to 4. What's the next one going to be? X equals 0? Negative, well, sorry. 0 minus what? 0 minus 1 squared plus what? Y plus 3 squared plus z minus 2 squared is equal to 4. So you're literally just doing the, oh, z equals 0. So that's going to be x minus 1 squared plus y plus 3 squared plus 0 minus 2 squared. And then you see what these three things imply. Let's look at these three things. What does this simplify to right here? X minus 1 squared plus z minus 2 squared equals what? What? Negative 5. And let's talk about what that means. You have two things that are squared adding together. What does that imply? Therefore, what? No solutions. So does this sphere touch the XZ plane? Does not touch the XZ plane. Nice. Let's look at the next one. What's this next one imply? Oh, you end up with what? What do you end up with? 1 plus y plus 3 squared plus z minus 2 squared. So it equals 4. You can get rid of that 1. What is that? What shape is that? That's a circle, right? So when that sphere hits the plane, what does it turn into?
So is the plane like sliced?
Where does it touch it? It touches it in a circle. So think of the plane as floating right here. The sphere has penetrated a little bit. Where does it touch it? In a circle. Yes?
Why doesn't it equal 3?
What? Oh, it's 3. Yes. I hadn't erased it. You're absolutely right. It's 3. You got that? So it intersects it in a circle of radius, what? Square root 3. What's the center of this circle right here?
0,
Negative 3, 2. Yep, that's where the center is. So that sphere hits that plane and creates a circle where it touches it. Let's look at the last one here. What happens here? What do you end up with here? You end up with x minus 1 squared plus what? Y plus 3 squared is equal to what? What do you end up with? Simplify for me. 0. What's the only solution to this? So it was when x is 1, negative 3, and 0. So this sphere hits the plane in how many points? It's just tangent. It touches it once. These are the three ways a sphere could intersect a plane, right? It could not touch it. It could touch it in 1 point, or it could penetrate through, and what do you get? A circle. A circle. More than 2. More than 2. Okay. More than 2. Oh, it's exciting. Okay.
It's literally just a point. Like,
Yes.
it has no space.
Literally, it's like a ball sitting on this desk. If a perfect sphere was sitting on this desk and this was a perfect plane, how many points would it touch? 1.
But it has no space to it. It's just a point.
It's just a point. It's just tangent. Like it's a ball. It's like it's.
But it's not like a ball. Because a ball consumes
This would be a sphere.
space.
A sphere. If this sphere is sitting on a plane, it's touching it in 1 point.
Yeah, I see.
That's what I mean. Perfect sphere, perfect plane. Okay, so here's the thing. We're going to graph surfaces where we're going to have 2 inputs, x and y, and we're going to have an output. Remember that temperature map we saw? It could have been it was topologically done. It had the boundaries. Could we make a height of 80 at 80 degrees, a height at 70 degrees, and have a surface? Absolutely. When we graph these things, when we come up with tables, we're going to have inputs of x and y and an output of z. That's our traditional way of doing this. So our tables are going to look like this. X across the top, y going down. So I could ask you, what's this value? Can someone tell me what that value is going to be? What goes right there? 13. Does that sound right? 13? I think so. What about this one? 32. So could you fill all these in? Okay. What's the function? X squared plus y squared. So here's the thing. Math, algebra in this, not that bad. Conceptually, be careful. Now, could you graph as many of these points as you wanted to? Graphing points and connecting them, is that the way to graph 3-dimensional graphs? What do you think? Almost never. A few times it's useful. Almost never. Here's the thing. If you started graphing all these points, what's gonna happen? Quickly, it's gonna look like what? A mess. Exactly. So it's not about graphing a point, 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 and trying to shade it like a machine. When you're graphing these by hand, you graph key aspects and you connect them with a minimal amount of lines and curves. Here's how. Well, actually, before here's how, what does this look like? If I were to look at this surface, if this surface was floating in front of me, what is it going to look like? Use your hands. What do you think it's going to look like? If I graph this, what's it going to look like? It's going to something like this. Does it go through the origin? Does this surface go through the origin? Yeah. Oh, come on, you can do it. By graphing specific pieces. So if I set up the axes right here, you'll notice here are, which 2 axes are these? Z and Y. When I draw the x-axis, don't draw it at 45 degrees. Anybody want to tell me why? If you draw it at 45 degrees, what happens to the 3-dimensionality of that picture? It goes away, it flattens it out. So I like drawing it at like 30 degrees. Makes it look a little better. So if I'm looking at the function f of xy is equal to x squared plus y squared, let's look at the planes, the coordinate planes. Let's look at the yz coordinate plane. That's when x is what? So that's going to be f of 0 comma y. What is that going to be? Z squared. Oh, y squared. If I were to graph y squared, let's say green on this. So y squared, what's that going to look like? It looks like this. Do you agree it's on that plane? Do you see what plane that's on right there? Like that? I'm going to get rid of that. Too many lines, it gets bad. What's the other plane I should use? How about the xz plane? The xz plane is when what is 0? Y is 0. So that's going to be f of x comma 0. So that's what? So what does that look like? It goes up like this, and it goes up like that on the xz plane. So what does this look like, everybody? I'll use green, black. So what's it look like? You see what it looks like? There it is. Rotational solid. There it is. It's a parabolic bowl. Thank you. Thank you. It's a parabolic bowl. Don't use too many lines. Your tendency is going to be like try to shade. The second you start shading, it starts like melting. It's like a Dali painting. You're like, what is it? I don't know. When you graph these by machine, by computer, you can do it at different densities, like different sampling rates. Like these are if you take at a certain density, it smooths out. The reason these are here is so that you can see the other sides, because if you do it all the way around, it's really hard to see. Perspective is hard unless you can manipulate it, but does that match what we drew? Yeah. When you take cuts parallel to coordinate planes, you're going to see parabolas. What happens if you cut it? What happens if you cut it?
It's a circle.
It's a circle. Exactly.
Up to a point, right?
Yes.
You get the high on Z.
Well, no. These extend. These planes keep on extending. Those are just emphasized. Those are cut so you can see the other side.
I see.
Okay. So, what happens when you start adding things in? So, like this is a bowl, but what happened to this bowl on G? What's the only thing that's happened? Shift where? Up 3. That's it. It's up 3. The bowl went up 3. That's it. What about this one? What happened here? It's almost the same. Facing down. But it's up how much?
5.
Yeah, because this is 5 minus x squared plus y squared, right? So what is this? It starts at 0, 0, 5, and what does it do? Goes down. That's it. That communicates to me you understand what's going on. Should you be doing this? Like, no. What about this one? What happens here? Which direction? Yeah, plus 1. Which direction? That's not a direction. Positive y. So right 1. If you're looking at it from the front, our front direction, if the x-axis is coming at us, positive y. The way we're going to label the room is this is the y-axis, this is the x-axis, this is the z-axis, and this is the positive octant. So when we want to move around in the room, that's what we'll do. Are you raising your hand and or stretching? Just stretching? Okay. So you might ask yourself, though, well, first, here's some more pictures. Remember those slices I was talking about? Years ago, a friend of mine. So if we do the YZ cross-section, that's when x is what? 0. So that's g of 0y. So that's what? Negative y squared. XZ is when? 0. So that's g. Oh, let me write it properly. G of what? x0. So that's x squared. If you're to graph those two things simultaneously, you have z, y, and x. Well, on the YZ plane, you have this. So what's it going to be? It's going to go down like that. Everybody okay with that on the YZ plane? But what about the XZ plane? It goes up, right? So those two paths both exist on that. So what does that look like? What sort of surface is, if there's a bend in it, right? Of some kind? It's hard to see. So what you do is you plot it. Here it is, my favorite surface of them all. It is currently folded and tacked to the math team bulletin board. It's called a hyperbolic paraboloid. Look what's going on, everybody. Remember, there's the origin, what's going on? There's the upwards parabola, and there's the downward-facing parabola. What was that first moral of the story with multivariable land? I told you you could either have a direct extension or something new, right? It's like Pringle, yeah. It's Pringle, exactly. Okay, I'm at this point, right? You see this right here? Let's say I'm walking on this path right here. What's the concavity of that path? Okay, well, what happens if I start at the same point, but I go side to side? What's that? What's the concavity at that point?
0.
Points either have positive concavity or negative concavity, right? That's we talked about that.
Yeah.
Yeah. Oh wait. Oh my gosh. Oh, what's going on? It's a concave up or concave down. Here's something that's new. Every single point on this plane, depending on what direction you're going in, can be concave up or concave down. Look, what happens if I'm right here? Concave up, concave down. So is this something new? Yeah. This is specifically called a saddle point, where depending on what direction you're going in, and this is probably the biggest epiphany you could have. Ready, everybody? When you're on a two-dimensional graph, you can go left and right. Remember? Left and right. How many directions can we walk in now? How many? An infinite number. Look, we could walk in this direction. We can walk in any direction we want. I can now walk in any of these directions. Is that going to change a lot of options for us? Uh-huh. Yeah, it is. Yeah, it is. This is my favorite surface. I love it. Love it. And we're going to fold it. It's super fun. Super fun. You can look at the folded hyperbolic paraboloid. It's sticking out of the math team board. Anybody know what I use to graph this? You have access to it. It's free. There's probably many, many places, and that's probably it. But no, this is from Wolfram Alpha. You can literally type in x squared plus y squared, and it'll spit out a hyperbolic paraboloid. You can manipulate it, zoom in and out. It's pretty cool. Okay, let's have a little contest here. Clear your desk of everything. Just clear your desk of everything. Everything. I want to bear it. Where do we like to find points when we're making lines? Intercepts, right? So we have the x-axis, we have the y-axis, and we have the z-axis. The x-axis is when yz equals 0. This is when x and z are 0, and this is when x and y are 0. So can you find me the three intercepts? What are they? What is the x-intercept going to be when y and z are 0? What's x going to be? That's a number. Can someone tell me what the point is? -1, 0, 0. Where does that come from? Well, I told you when y and z are 0, so it's going to be 0 equals 1 plus x plus 0. What does x equal? What does that? -1. So what's the point for this one? -1, 0, 0. Can you find the other 2 points for me? Find them for me. Find the other 2 intercepts for me. Find those 2 intercepts for me right there. Those 2. Find those 2 intercepts. What are the other 2 points? Anybody have the? What's someone who hasn't spoken yet? What do you got, Wiley? What's the next point?
The y is going to be 0, -1, 0.
0, -1, 0?
Yeah.
You sure?
Yeah.
0, 1, 0.
Isn't it 0, 1, 0?
Well, if you plug in 0.
Yeah, you plug in 0 for x and z, so it's going to be 0 equals 1 plus 0 minus y. What makes that true?
Oh, that's minus.
It's a minus right there. Minus. You see minus?
I put in a plus.
So what's the next one going to be?
0, 0, 1.
0, 0, 1. So how many points do we have? 3 points. We have 1 point, 2 points, 3 points. Let's graph those 3 points. If I graph those 3 points right now, I get z, here's y, and here's x. Where's the first point? Back here. That point right there is -1, 0, 0. What's that point right there? Someone tell me. What's that one?
0, 0, 1.
0, 0, 1. And then we also have 0, 1, 0. What do you do once you have those 3 points? Connect them. There is your plane right there. Is that only a piece of the plane?
Yeah.
Yeah, what does that plane do? It extends infinitely in these directions. Imagine if we had a triangle piece of wood propped up in the corner here. Is that a plane? It's only that piece of the plane though. So when I ask you for a graph of a plane, this is how I want you to graph it right there. That's how I want you to graph it.
It continues.
Yeah, you see the arrows?
Yeah.
The arrows. It keeps going out.
So it would be like.
Imagine you had a triangle and it just the piece of plywood keeps going out.
Floating triangle on the other side.
Yeah. There'll be no. It just keeps going. Imagine this triangle just getting bigger like this.
Yeah.
But this is the angle it's cutting in that octant. That's the part that's in that octant right there.
Yeah.
What happens here? What happens if I changed it to z is equal to y squared?
It's just taking itself. Yeah.
What's missing in there? X. So instead, you're going to have it going up like this, up like this, up like this, like this.
I have a question.
It would turn at 90 degrees. Yes.
Does that theoretically go on?
Yes. It doesn't stop. It keeps going. Yes. This edge keeps on going. Yes. Both directions. This is just a piece of it. Over here, let's say I changed it to x squared plus z squared is equal to 1. What's missing? So what would happen now? You would have a circle around the y-axis. It would turn into a cylinder like this. It's not drawn very well there. It would turn it. Because what's missing? Oh, the y. So it doesn't matter what y is. It would go around the y-axis. It's a circular cylinder. Nice. So what does this look like in 3 space? Well, it looks like that right there. Is that pretty exciting?